So during the last PowerPoint, we discussed the concept of osmotic pressure, and osmotic pressure is described as the pull solute molecules have on water. And the more solutes you have, the stronger your osmotic pressure will be, and the more water will be moving through the means of osmosis. Now, using that concept, we are going to discuss the process or concept called tonicity. So tonicity is the ability of the solution to change the shape or tone of the cell by basically moving water either inside or outside the cell, or movement of water inside or outside the cell at a similar level. The other concept you also need to understand is that your cell has limited capacity, which means that it can gain or lose water up to certain amount, but anything beyond that will disturb the function of the cell, and as a result, your cell basically dies. So let's keep this in mind, and let's take a look at the situations that you can place your cells in, and how those situations affect the shape of the cell and its activity. So we have three words here: isotonic, hypotonic, and hypertonic. Iso is described as equal, hypo means below, and hyper means above. The really key concept when we're talking about tonicity, and I really want to highlight this point, is that these three words, isotonic, hypotonic, and hypertonic, can only be used to describe solution, the environment the cell has been placed in. So if I'm describing a scenario like this, and this is my cell, I can say, let's say 200 milliosmolarity versus 100 milliosmolarity. And if I was to describe this solution, what I would say is I first compare the osmolarity of these two solutions. So this is 100, this is 200. So I'm going to put an arrow and it says 200 is a larger number, so it's a bigger number, and 100 is a smaller number. So I'm going to use one of these three words to describe what type of solutions I have. So by looking at that, 100 is a smaller than 200. So my solution would be below, or the solution is a smaller concentration of solute. So I will identify this as hypotonic. Now, in a scenario that I'm describing here and using the concept of osmotic pressure, you should understand that the more solute I have inside the cell, the more water I'm going to be moving into the cell. So this arrow represents the movement of H2O into the cell. And if I'm gaining water inside the cell, basically that causes my cell to swell. And if there's too much water moving into it, it will cause the cell to burst. Now, let's take a look at these scenarios and how they affect your typical cell. Again, remember that these words, hypotonic, isotonic, and hypertonic, only and only can be used to describe the situation for your solution and not your cell. So, the word isotonic. So, starting with the concept of isotonic. Solution has the same osmolarity as inside the cell, so volume remains unchanged. So let's draw this out. So let's say I have a solution. This is my cell inside of it, and I'm just going to give it a number. The number is milliosmolarity units, so concentration basically. So I have 100 there and 100 here. Oh, whoa, whoa. My computer has a mind of its own apparently. Sorry guys. Wait for 1 second. So again, basically what I will have is a scenario where I have a situation. I'm going to make my number smaller. Let's just say 100. 100 for the cell, 100 for the outside environment. So this is equal concentration, therefore equal concentration or equal osmolarity for inside and outside. So water will be moving in and out of the cell via osmosis. However, because the amount of water moving in or out of the cell is equal, then there is no change in the cell shape because you're not gaining or losing any water. Now, the second scenario we have is a hypertonic. So let's look at an example for hypertonic. So I have a solution. This is my solution. Let's give it a number 200. And let's say my cell is 100. So 200 is a larger number, so I'm going to put the upward arrow. And 100 is a smaller number, so I'm going to put a downward arrow on it. So looking and comparing these two between each other, this is a larger number. So my solution compared to my cell is a hypertonic solution. Hypertonic solution that has a higher osmolarity than the inside the cell, 200 versus 100. So because I have a higher number of solute particles, what happens is water is going to move out of the cell. And if your cell is losing water, it causes the cell to shrink, if you use the word crenation for it. So if your cell is placed in a hypertonic environment, your cell will shrink. If it's placed in an isotonic environment, the cell keeps its original shape. Now, in the last scenario, what I have is a hypotonic. So if you draw in a similar situation, so let's say I'm going to give 100, and again, I'm going to write the unit this time, milliosmolarity, and inside the cell, let's say 150 milliosmolarity. So in this scenario, your 100 is a smaller number and your 150 is the larger number. So in comparison, your solution has less solute molecules, therefore it is considered to be hypotonic. And thinking about it in the sense of osmotic pressure, because you have more solute inside the cell, water is going to be pulled into the cell, and as a result, your cell is going to start to burst, it starts to swell, and if the water is moving at a higher rate and it continues to moving, it can cause the cell to burst, which we also use the word lysing, or basically destruction. So here is the three situations that we described. What you have first, you have your regular red blood cell. So in this case, notice that the arrows are equal arrows moving in and out of the cell, which means water is still moving via the osmosis process, but it's an equal amount, and consequently your cell shape will not change. So your red blood cells keep its original shape. Second scenario, you have a hypertonic. So hypertonic implies you have, again, if I'm drawing this in this sense, let's again use an example here. We have a 200 versus a 100. So 200 is more, right? So you're hypertonic, and water is going to be pulled out, as you can see the arrows, and that causes the cell to basically shrink or crenate. If you describe the last scenario you see here, what you will have, let's say you will have 100 here and 150 here. 150 is a larger number compared to your outside, so this is a smaller number and therefore it's hypotonic. Water is going to move in via osmosis because you have more solute inside the 150. That causes your cell to go from the relative size, the normal size cells, to basically increase in size. It's going to swell, and if it continues to swell, eventually causes the cell to lyse. Something that I need you guys to know, and this number is essential for you guys, is that your environment in your body is considered to be isotonic, because you don't want your cells to basically undergo continuous change. Now, the environment is created by a 0.9% salt solution. That is the normal concentration of your inside the cell and outside the cell. So that's something that you need to know. It will help you guys understand the concept, or the, I guess, in a sense of nursing, how does this change in the concentration, if you're dehydrated versus overhydrated, affect your cell shape. Now, last one I'm going to talk before we finish this PowerPoint is this presentation, is the concept of tonicity versus concept of osmolarity. So, as I mentioned, we can use the word osmolarity to basically describe the concentration of solutes, and it doesn't matter if it's inside the cell or outside the cell. I can use the concept of osmolarity to describe both the cell or the solution. However, the word tonicity is limited to only and only solution. So I cannot say my cell is isotonic. I can say my solution is isotonic, but I cannot say my cell is isotonic. So here is a scenario that's given on your PowerPoint. You basically have a cell that has 100 milliosmolarity, and your solution has 200 milliosmolarity. So we can use the word tonicity, or the concept of tonicity, to describe this. So this is a larger number compared to this one. So this would be a solution, would be a hypertonic. Sorry about the motorcycle. The solution would be a hypertonic solution. But I also can describe both of these in a sense of osmolarity. So my solution is also going to be hyperosmotic, and my cell would be hypoosmotic because it has a lower number. But notice that I draw a red line. You cannot say your cell is hypertonic. So let me draw a scenario for you guys, and we can get some more practice. So let's say I have 100 here and 200 here. So if I was describing this scenario, what I could say is, looking at the number, this is a lower number, this is a larger number. So for the solution, I can say the solution is hypotonic solution. I can say the solution is hypoosmotic solution. And I can also say that your cell is hyperosmotic cell. And notice I'm not saying hypertonic cell. We're just limiting it to the concept of osmolarity and in a sense of osmolarity. Okay, so this is the scenario I was explaining to you earlier about the 0.9%. Within your cell, you have an environment that is considered to be isotonic. So if you are giving a blood transfusion, typically that would have a concentration of 0.9% or 0.9 gram per deciliter. And this is a normal saline solution made up of NaCl, which is basically a salt. And again, this is normal osmotic concentration for your extracellular fluid, or ECF. If you have a hypertonic solution, hypertonic solutions are usually given to people that are swollen. So what this hypertonic is going to do is going to create a higher solute environment around the cell. And that hypertonic environment is basically going to pull water out of your cells and back into your bloodstream. So it basically brings water back into your bloodstream, and rather than the environment surrounding your cell to take the swelling away. Typically, this is a solution that is a combination of saline and dextran, which is basically a form of sugar. dextran cannot pass through your plasma membrane, so it stays inside basically your plasma or the fluid part of your blood, and it pulls the water from your interstitial fluid back into your blood plasma. Hypotonic solution should not be given to any individual, because if you create a hypotonic environment, you're basically allowing a lot of water to get into your cell at a very rapid pace, more specifically your red blood cells and white blood cells. And if these water moves into your cells, it causes the cells basically to swell, to swell, and eventually burst if the movement of water is significant enough, which is basically the scenario we're describing in the last case, which is a hypotonic solution. Okay, I'm going to end this PowerPoint and then we'll pick up the active transport on the next presentation.